Hi, this is the preview lecture for lecture 9, and up to now we have succeeded to implement nonlinear Poisson equation solver. So we have applied it to one-dimensional double gate structure. In 2 years ago, we just moved to Schrödinger Poisson equation. However, I feel that now we have to think about two-dimensional implementation of this program. So that's the reason why our lecture 9 is devoted to the implementation of two-dimensional Laplace equation solver. Okay. So think about Laplace equation in two-dimensional structure. In this case, we will consider xy plane. In this case, our Laplacian operator now contains the partial derivative with respect to x direction and the partial derivative with respect to y direction. Okay, now we have two different operations. Since now we have the Laplacian, the Laplace equation can be easily written as this form. Laplacian of our solution function phi should be 0 everywhere. Of course, we need boundary conditions. In this lecture 9, we will consider a very simple example. So consider a rectangle, yes, and common spacing along x direction and y direction will be assumed. So here and there we have a spacing of delta, also delta, and also in y direction we have a uniform spacing delta and delta. And along the x direction, we are assigning n sub x points, and along y direction, we assign n sub y points. So they can be different. And mixed boundary condition will be considered later. It means that in this box, some of them can be specified with Dirichlet boundary condition, and for others, we apply homogeneous Neumann boundary condition. That is the mixed boundary condition is considered in this work. So we have to first build a solution vector. At first glance, it is quite natural to build a solution matrix. However, we should build solution vector. So anyhow, our points should be aligned in a certain order. So in this example, we just propose to assign them in the following order. This one becomes 1, the first one, 2, 3, 4, 5. Its index ends at n sub x. After that, the second row is assigned with n sub x plus 1, n sub x plus 2, and n sub x plus 3. It ends with 2 sub x. Think about a certain point which can be expressed as a pair of ix, iy. So in this case, what will happen? So here we have iy's row, and this is corresponding to ix column. So in this case, we have actually I y minus 1 rows which is completely filled. We have I y minus 1 times nx. Actually, it is corresponding to number of points in these completely filled boxes, and remaining thing is, okay, we have ix points filled up to now. So we have ix. In the vector notation, that will be the correct index for a point corresponding to ix, iy. So this is written in here, and of course, if you wanted to do it differently, for example, you can follow the order like this way. If you prefer this way, it is up to you. You can follow any way to assign your unknown variables in a vector, but don't be confused with different ways. So if you select one way, then you should apply it throughout your code. Once you do it in a consistent manner, then everything will be quite okay. So now let's say that you can easily find the index inside your solution vector. Then first of all, we have to assign the discretized form of our Laplace equation. So how can we proceed with this two-dimensional example? The Laplace equation for given node, let's say that this is nothing related with the boundary, it is away from boundary, so always we can find many surrounding points around it. Then the Laplace equation is integrated over its control volume. So in this case, we just consider this integration. Let me do it together with you. So we have Laplacian of phi equal to 0, and when we make a volume integral of this Laplacian of phi over certain volume, and by the divergence theorem, then we can easily say this becomes surface integral, and there is some dot product between gradient of phi and infinitesimal area component. Then it should be 0. So that is written here. And this is the left hand side of our Laplacian equation, and that should be 0. That is all for our implementation. So now we wanted to make a discretized form of this surface integral. How can we do that? So let's just convert it to the discretized form shown here. Since we have surfaces here first, second, and third, and fourth, we have 4 surfaces. So our surface integral can be decomposed into 4 different integrals. And here, since dA is a vector component, for example, when we consider this surface, then now dA can be approximated as just delta, which is corresponding to the length and x directional unit vector. That is the approximation for our dA component for this right surface. And how about our gradient of phi? of course, gradient of phi can have its x-directional component and y-directional component. But if we have y-directional component, that doesn't matter because we make the dot product between dA, and you know that dA is aligned with the x-directional unit vector. So important thing is now our gradient of phi dot dA just becomes x-directional component of our gradient phi multiplied by just delta. Then how can you approximate this gradient of phi, its x-directional component? It can be easily approximated as phi I plus 1 comma j minus phi I comma j. You know, this is corresponding to phi I plus 1 comma j, and this is corresponding to phi I comma j. And take the difference and divide it by the difference between them. This is simply delta, because we have assumed that the uniform spacing along x direction and uniform spacing along the y direction and happen to be they are identical. So we have delta here, and here we have still delta. They are gone. So the contribution from the right surface simply written as phi I plus 1 comma j minus phi I comma j. Then what will happen to other surfaces? For example, if we consider the left surface, you can easily find that this is contributing phi I minus 1 comma j minus phi I comma j. Even when you consider this top surface, that will just contribute something like phi I comma I plus 1 minus phi I comma j. Now you can easily understand every surface just to contribute something related with its direction minus the center node quantity. When all of them are considered together, you can find that there is 4 times of phi I comma j, the center node quantity, and 4 surrounding node values corresponding to right surface, left surface, top surface, and bottom surface. So you can easily understand this form. And one thing you can easily understand also is when we introduce different spacings along x direction, delta x, and y direction, then only difference is now it has certain numbers corresponding to, for example, delta x over delta y or delta y over delta x, depending on its direction. Okay, so you can understand it quite easily. However, up to now, everything is quite clear, but this is related with a node which is not corresponding to a boundary. So if we have boundary nodes, then we need special care for them. So let's go to the boundary conditions. In in this lecture 9, we consider a very simple toy problem. As shown here, we have just 1, 2, 3, 4, 5, 6, 7, 8, 9. And along x direction, we have only 9 points, and 1, 2, 3, 4, 5. Only 5 points along y direction. Then here the properties of each point are written with different symbols. For example, empty circle means that this is just corresponding to a bulk node. So the treatment can be found in the one in previous slide. So it's okay. And now we have 3 more circles. One is corresponding to black circle, and this is this one, and this one, and this one is corresponding to homogeneous Neumann boundary condition. So for example, normal component of our gradient of phi should vanish in these points. So this is typically used in our semiconductor device simulation. That is quite frequently found in our real example. And blue circles, in this case we have applied just 0 and 0 for them. And finally we have red circles. So here we have assigned the values, but the difference is for these ones we have applied the number 0, and here we have applied non-zero values, for example unity. But anyway, these two circles, blue or red circles, can be categorized as a Discrete boundary conditions. So, shortly speaking, we have already covered bulk nodes. It's okay. Now we have to consider Neumann boundary condition and Discrete boundary condition. Let's do it together. So for Discrete boundary condition, either that is 0 or 1, that doesn't make a big problem to our consideration. So it's not difficult to consider the Discrete boundary condition. How can you do that? For all ix, iy, so this is a typo. So we simply have phi is assigned to 0 or phi is assigned to 1. That's it. So then when you just make your Jacobian matrix, then you will have just number 1 for your certain diagonal component, and just that's it for your Jacobian matrix. So and in the case of this red circle, still you have number 1 for Jacobian matrix, and residue vector, of course you have certain non-zero term corresponding to unity here. And more tricky one at a first glance is the Neumann boundary condition. Consider a node with a black circle. So typically we can find it in our structure at left boundary, top boundary, and also right boundary. In order to make our discussion concrete, let's concentrate on left boundary, but you can apply the same argument to top and right boundary when the homogeneous Neumann boundary condition is applied. So in the left boundary, now you have certain points. For example, if this is your center point, then this is just specified as 1 comma I y. So this 1 is corresponding to the left boundary. Of course, if you are considering the situation at right boundary, then you will have a pair of nx comma I y. That is quite obvious. And now your box should be smaller. Previously, for example, for this bulk box, you have this square whose length is delta and delta along x direction and y direction. But for your boundary nodes written in these lead boxes, now its x directional length is just half of delta, while y direction length is just delta, just as usual. So for this smaller box, how can we consider the integrated version of our Laplacian operator? Let's do it together. Still, we will have 4 boundary surfaces. So this is a center node corresponding to 1 comma I y, and we have 4 surfaces corresponding to top surface, bottom surface, and right surface and left surface. But you know that for these boundary nodes following the Neumann boundary condition, actually the integration over this left boundary vanishes. That does not contribute to our discretization. So now we are allowed to just consider 3 different surfaces only. Okay, so let's do it together. So how about this right surface? Here we will have 2 times IY. Everything is just the same as before, so it will contribute, for example, phi 2 comma IY minus just phi I 1 comma IY. So that's it for our right surface. But how about this top surface or bottom surface? In this case, the area is not corresponding to delta, but we have to have just half delta, because this is corresponding to delta and this is just corresponding to half of delta. So we have half of delta, and on top surface we have something like 1 comma IY plus 1 point. So for this one, the gradient, y directional gradient, now becomes phi 1 comma IY plus 1 minus phi 1 comma IY divided by delta. It is quite understandable, and this delta and delta are cancelled out, but you know that here we have number 2 here remaining. So contribution from the top surface is just half of the normal surface, like a light surface. So in this case, we have to write down something like this: half of phi 1 plus IY plus 1 and minus half of y. And how about this bottom surface? They are identical to the top surface, so we will have just half phi 1 comma iy minus 1 minus half of phi I comma iy. So now you can clearly see that when we apply the boundary condition, homogeneous boundary condition to the boundary node, then our expression is a little bit modified because the box is smaller and the left surface does not contribute. So you can see that now the central component becomes, instead of minus 4, now we have minus 2, and we have a slightly modified values. At the first glance, it looks a little bit tricky, but anyway, you can do it. You can do the manipulation for your left boundary and right boundary and top boundary. Then you can have similar equations, but with different numbers for different indexes. Please do your exercise for each boundary. When you build the Jacobian matrix, you should be careful. Don't make mistakes in the manipulation and implementation. So my suggestion is an edge-wise construction, but anyway, it's up to you. When you do it just correctly, then any implementation manner is just okay. So now you have homework number 9. So as usual, you have 2 days to solve this homework. Today, we have introduced a toy problem where nx equal to 9 and ny equal to 5. So, but anyway, you can make a simple Laplace equation solver for it with given boundary condition. And now I wanted to ask you 4 different cases. Red circles, the first one is red circles are located in the original position. So what is it? So it is corresponding to our original problem. The top right surface is set to be 1 and all other are set to be 0, and homogeneous Neumann boundary condition is applied. So the original problem is our sub-problem, the first. And second one is red circles are located in the top left position instead of our original problem. Now we wanted to solve just swapped one, like we have 1 and 0, and still our bottom contact is set to be 0. And third one is the red circle are located in the bottom position. Okay, now in the third sub-problem, instead of these two top contacts, now we have bottom contact, which is set to be 1, and they are just given as 0. So up to now, I just propose to solve 3 different Laplace equations with different boundary conditions, each of them corresponding to this one becomes 1, this one becomes 1, or this one becomes 1. And finally, all 3 positions or all 3 contacts are biased with number 1. So then please make a comparison between your answer for first sub problem and 1, 2, 3, and draw 3-dimensional graphs for each of them. Please note that this is just a Laplace equation, so therefore you don't have to worry about non-linearity. So this is just a one-shot problem. You can just to solve it once, ax equal to b system once, then you will get the solution. Of course, we will move to more difficult problems in lecture 10. Okay, see you Monday. Bye.